Good morning, all. My name is Nitin Tomar. Today, in this session, we are going to discuss some problems from complex analysis assignment. And so, just we start. So, here onwards, omega will be a domain in a complex plane. In the complex plane, by a domain, we mean an open connected subset. And the C of omega will be the space of all continuous function on omega, and H of omega will be space of all holomorphic function on omega. Okay. Now the first question is, if f is in C of omega such that integration of f over this gamma is 0, and this holds for every closed curve gamma in omega, this holds for every closed curve gamma in omega, then f is holomorphic. So this option is true. This option is true. This option is true, and that is precisely what we call Morera's theorem. Morera's theorem. No. So what does Morera's theorem say? It says if integral of a continuous function over any closed curve gamma in omega is 0, then f has to be holomorphic. And in the second question, it says it is exactly the same as the first question, with the closed curve being replaced by a triangular path. And by the homotopy theorem and Morera's theorem, because any triangular closed path is same as homotopically they are equivalent. So if f is in C omega such that integration of f over gamma is 0 for every triangular path, for every triangular path gamma, then f is holomorphic. This is also true by Morera's theorem. So these two parts of first question are just some variants of Morera's theorem. Okay. Now, see, the third and fourth question are quite similar, except for the fact that the convergence in one question is pointwise, and in the second question, the convergence is uniform convergence. Okay. So the question read as, if fn is a sequence of functions holomorphic in omega such that fn converges to f pointwise. Remember, in the question it is pointwise, in the third question. Then f is holomorphic. And in the fourth question, the convergence has been replaced by the uniform convergence. So, fourth question asks if fn is a sequence of holomorphic functions in omega such that fn converges to f uniformly in omega, then f is holomorphic. So, let us first recall what does pointwise and uniform convergence mean. Recall. So, first is pointwise convergence. So let's say fn is a sequence of fn is a sequence of functions defined on some set omega. Okay. So pointwise converge. Just a minute. So how does fn look like? Each fn is, it's a function. It's a sequence of function, and let's say f is some function defined on omega. Then we say, so this is for the pointwise convergence. This is for the pointwise convergence. We say fn converges to f pointwise if for every z in omega, for every point in omega, this sequence f and z converges to f of z as n goes to infinity. See, just remember that now when you supply points to the sequence fn, so this f and z, this f and z, so this is, so for every z in omega, for every point in omega, you will have a sequence, and that sequence is a sequence of complex numbers. So this is a complex, these all are complex numbers, and this is also complex numbers. So pointwise means for every point, the sequence of complex number f and z converges to the complex number f of z. If this holds for every z, then we say that the convergence is pointwise. And for the uniform convergence, so if we write in epsilon delta form, if we try to write this in epsilon delta type, then we'll get, and for the uniform converge, so for the epsilon in epsilon delta term, so first we fix an epsilon for a, like this is the raw idea, and for epsilon delta term we say for a given z in omega, and epsilon greater than 0, there is a stage, there is a natural number, there is a natural number n that depends on this epsilon as well as z, such that mod of f and z minus mod of fz is less than epsilon for all n greater than equal to this n which depends on epsilon and z. So one thing that you have to note is that this stage, this capital N stage, this depends on the epsilon as well as the point. If you change your point, your stage will change. If you change your epsilon, your stage will also change. So n is a function of two variables. Now second comes the uniform convergence. Uniform convergence. So uniform convergence is again, so given z in omega and epsilon greater than 0, there is there is n, now it depends only on epsilon. Okay, there is a natural number n such that f in z minus f of z, this is less than epsilon for all n greater than equal to n which depends on epsilon, and for all z in omega. So we say fn, this sequence converges uniformly to f on omega if for given n, for given z in omega and epsilon greater than 0, there is a stage which depends only on epsilon, such that the distance between fn and fz can be made smaller than epsilon for every n after this stage, and this holds for every point. So the the only difference, and which is the big difference between uniform convergence and pointwise convergence, is that in pointwise convergence, if you change your point, your capital N will change, it might change. And in the uniform convergence, the stage is independent of your choice of the point. So one immediate upshot of these two definition, which I'm writing as remark, is the following: that pointwise convergence is implied by uniform convergence, is implied by uniform convergence, whereas pointwise convergence need not imply uniform convergence. Okay, so some result. So there are so I'm writing them as remark only, but these are very standard result. Uniform limit, uniform limit of a sequence of continuous function, of a sequence of continuous functions on a domain say omega, on some set omega, is a continuous function on omega, is a continuous function on omega. Okay, now we prove. So what we have been asked to prove in the question is that the uniform limit of a sequence of holomorphic functions, holomorphic functions on omega, is again a holomorphic function in omega, is a holomorphic function on omega. And how do we prove it? We prove it via Morera's theorem. So this is the proof that we are going to discuss. So assume that fn converges to fn converges to f uniformly on omega. So this we have assumed. Now the first point that you should know, that since each fn is holomorphic in omega, hence it is continuous in omega. And as we know that the uniform limit of a sequence of continuous function must be a continuous function. So therefore the limit function f is also continuous. So this is precisely the first point, because to start with holomorphicity, we have to prove that a function is first of all a continuous function. So f is a continuous function now. Now we'll use Morera's theorem to prove the holomorphicity. So we have to show that f is holomorphic in omega. Okay. Now we will use Morera's theorem. We will use Morera's theorem for that. Morera's theorem. So our aim is to prove that for any triangle T in omega, the integration of f over this triangle is 0. Okay. So how do we prove it? So you start with integration of f over this triangle T. You start with any arbitrary triangle T and consider integration of f over this triangle T. Then write, because f was what? F was limit of fn, uniform limit of fn. So we just put the values. Then we know that the with the uniform convergence, you can actually interchange the limit and the integral. So hence this limit will come out. This limit will come out. So we have limit integration of fn over d omega over a triangle. Now, because fn is a holomorphic function on omega, an integration of a holomorphic function over any closed curve inside the domain in which that function is holomorphic is 0. Okay. So all of these integrals with integrand is fn is going to be 0. So the limit of 0 sequence is 0. So hence we have proved that integration of f over this triangle T is going to be 0 for every triangle T in omega. Hence Morera's theorem will imply that f is holomorphic in omega. So one thing that we have used here, which we see, the part where uniform convergence is used is precisely this part, right? Had it been the pointwise convergence, we would not have been able to interchange the limit and the integration. Okay. So to answer those questions, so fourth is true, fourth is true. Oh, sorry, fourth is true, and I'm writing false. No, fourth is true, and third is false. Okay. See, for the pointwise convergence, even a sequence of continuous function may not have the limit as a continuous function. So we can construct one example so that I leave you as an exercise. And in the proof also we realize that pointwise convergence is not enough. So it must give you some sense of strong intuition that with pointwise convergence we will not be able to go further. Okay. So let's move to the next question. So for the next question, let us fix our domain. So let us fix our domain. So D is this fancy D is the open unit disk, and so with this we move to the fifth part, which is if D plus, so D plus is this, so D plus is the domain, is the subset of open unit disk whose imaginary parts are positive. All those complex number lying in the open unit disk whose imaginary parts are strictly positive. So it is like the green portion of the open unit disk. So in the figure, so if this is the figure, let's say figure 1. So in the figure 1, D plus is precisely the upper half part of the open unit disk, and D minus is the lower half part of the open unit disk, which is the set of all complex numbers lying in the open unit disk whose imaginary part is strictly negative. Okay. Now the question that have been asked is the following: if f is holomorphic in D plus union D minus, so f is holomorphic in the upper part as well as the lower part. So holomorphicity is not given on this line -1 to 1, this interval. Okay. And it says f is continuous on open unit disk. So continuity is given and holomorphicity is given except for a very thin part of the open unit disk. See, as compared to the open unit disk, the part where the holomorphicity is missing is a very thin part. It's just a line segment starting from -1 and ending at 1. and then we have to prove that this f is holomorphic in the open unit disk. See, whenever you have been given continue on the domain, so one thing to automatically apply is Morera's theorem. So we'll prove this fact by Morera's theorem. Okay. So our aim is to prove that integration of f over any triangle in the domain is going to be zero. Okay. So I add a picture here. So this is our disk. So this is our disk. So this is my open disk. Okay. And let's say this is the line where the, oh sorry, this is the line where the holomorphicity is not given. Okay. So this is my open unit disk. Hmm. Now D plus is the D plus is this upper half part. Okay. Oh, which color we have used? So that it just okay, green, huh? Yeah. So D plus is this part. The all those complex numbers which lie in the upper half part of the disk, open unit disk, and D minus, D minus is the lower half part. Okay. So this is my D plus and this is my D minus. So this is my D plus and this is my D minus. Now Morera's theorem will say if you prove that for any triangle, if you prove for any triangle, this integration of f over this domain is zero for any triangle T in omega, T in this D, then f is holomorphic in D. So remember the continuity is given. Now since f is continuous, since f is continuous on D, this is given. F is continuous on the unit disk on D. It suffices to show that this happens. Then Morera's theorem will give you Morera's theorem gives that. Then Morera's theorem implies f is in h of D. F is holomorphic in D. So this is our idea. This is the crux of the proof. So let's draw triangles. So if some triangle is here, then everything is fine, right? Why? Because f is holomorphic in D plus. So we do not need to consider these triangles. And if similarly if some triangle lies in D plus, D minus, then also we are done. Because f is given to be holomorphic in D minus. Now the only problem is if a triangle have some non-empty intersection with this line say L. Okay. So triangle can look like this, right? On this line, or it can look like this, or it can just intersect at some point. Okay. So let's say this is type 1, this is type 2, and this is type 3. See, type 2 and type 3, they can be deal with as follows. Uh, you just divide type 2 in further subtriangles. Okay. So this triangle is of type 1. Again, this triangle is of type 1. And the triangle here is type 3 triangle. Okay. So it suffices to consider only triangles of type 1 and type 3. Okay. Now see, the triangle 3 intersects the triangle 3 intersects the line at only one point, so it won't change the integration. The integration at one point won't change. So you can have this, for this triangle you can write, for triangle 3, you can have directly integration t f dz is 0. Okay. And triangle 2, the triangles in case 2 is a amalgamation of cases in type 1 and type 2. So now what we do, we consider only type 1 triangle. Okay. So type 1 triangle are like this, right? Okay, let me write. I'll draw another triangle. So type 1 triangle are like this. Yeah. And this is our line L. And this is D plus. Okay. So what you do, we try to approximate this curve. Okay. So if you take this triangle, let's say let's say this is A, B, these points A, B, and C. So this A1, so this A, B1, C1, this is a triangle, and over this triangle, the integration of f is 0. Why? Because it completely lies in D1. Then you go to again this triangle A to A, B to C2. So again, triangle integration of f over the triangle A, B to C2 is 0. So if you define your Tn, if you define your Tn to be the triangle A, B, N, C, N, then we know that this integration over Tn of f dz is 0, right? Now you keep on doing that. You keep on doing that. Okay. So you keep on doing that. So you will get a sequence. You will get a sequence. Okay. And as you see, because f is continuous and curves in these curves are continuous functions, right? So these curves a, b, and c, and they're approximating a, b, and c. So this you can prove that, this you can prove easily that this converges to f dz. Okay, this you can prove. So this is an exercise, and when you are, so one can prove that this integration of f t and f dz goes to integration of f over t dz by using uniform continuity of f. Now on the left hand side you have a zero sequence. So this integration will be 0, and because integration of f over t is the limit of a zero sequence, it has to be 0. And now since we have discussed all cases for the triangles, the Morera's theorem imply that f belongs to holomorphic function of D. Okay. So this question was all about Morera's theorem. Okay. So next we discuss some few questions on winding number. So what is a winding number? Given a closed curve gamma such that a point z0 does not lie in the image of gamma, the winding number, which we denote by W subscript gamma z0, is the total number of times the curve gamma travels counterclockwise, that is in the positive orientation around z0. Okay. And theoretically, we have this formula 1 upon 2 pi iota integration of gamma over dw by w minus z0. So in these examples, you see in the figure, in the first case, the winding number, the curve, the gamma is a closed curve, and z0 is some point which does not lie on gamma. So its winding number is 1. In the second case, because the direction is clockwise, so its winding number is -1. In the third case, you see the Z naught lies outside gamma, so its winding number is 0. And in the fourth case, the winding number of Z naught is 2. Because if you, let's say you start from here, then 1, so you have, sorry, yeah. So this is like 1, then 2, okay. So the winding number is 2 in this case. Because winding number also has this integration formula, so we can always check, okay. So the first question is, if the winding number is invariant under representation, the answer is true, because we have seen in the initial classes that integration is invariant under the representation of curve, and winding number has a formula which involves the integration. So this option is true. Second is, winding number, if you change the orientation it stays same, that is w gamma of z naught is w subscript minus gamma of z naught. We have seen, we know by definition, if you change the orientation, the winding number will come out to be the negative. So this option is false, okay. Now the third option is, winding number is locally constant on on the domain c minus gamma, and that is true. Why? Because if you take some point z naught, let's say here, you can always find a neighborhood disjoint from gamma, and in this neighborhood, in this neighborhood, you can see the winding number takes value 0. The winding number takes value 0. And similarly, if you take any point here, let's say, okay, let's say xi, and you draw any, you can have some neighborhood which has non-empty intersection, then in this neighborhood the winding number is 1, and you can do this for any point. So the winding number is locally constant, but it is not a constant function, okay. So yes, so in the end I want to give you some so it can take any integer value depending on your curve. For example, in this case, you can see the winding number at point xi, it is 2, because the curve gamma revolves around xi 2 times. The winding number at w naught is 1, and winding number at z is 0, okay. So these were the exercise about Morera's theorem and winding number. Hope you have understood it. If you have some doubt, then please reach out. You have my mail ID.